Good afternoon, all. This is Ken Watkins with PCB Piezoelectronics. This afternoon, I'll be presenting basics of piezoelectric accelerometer selection. And just to give you a little bit about my background, my role at PCB is technical sales specialist. And I've been with PCB for about 23 years. And my role is covering our tech sector, which includes automotive, test and measurement, aerospace, defense. And this afternoon, we thought it'd be beneficial to give you an overview of accelerometer selection in the event that it could help you select the right accelerometer for your application, given the vast availability of many different accelerometer models that are available in the marketplace. So with that, we'll go ahead and get forward. So topics that we're going to be covering are going to include selecting the right accelerometer, different types of acceleration, transduction, types of accelerometer technologies, Newton's second law.
Has joined the meeting.
Frequency response, both low and high, accelerometer construction as a background reference, mounting methodologies that can be employed, and, of course, typical applications which these products are used for, and just a quick application focus spotlight regarding using accelerometers in research and development. So with that, we'll go ahead and move on to the next slide. Accelerometers, where to start? So what is the kind of information that a typical test engineer is going to need to understand and acquire in advance of selecting the right accelerometer? So we put this together as to help from a location where to start. You know, whether you're just getting involved in testing and accelerometers or you're experienced with this product, we thought maybe give a good idea on where to start and how the process is of how we would typically
go joined the meeting
and recommending a product to fit various applications. So always we typically will ask what the application is, not because we're trying to be nosy, but trying to understand how the product's going to be used, so that we can make sure that we're pointing in the right direction and from a product perspective. And then there's both single and three-axis accelerometers. I'm referring to X, Y, and Z, Z being your predominant single axis, and of course the three-axis would be all three orthogonal axes. Event magnitude, whether that be in terms of Gs or meters per second squared, what kind of frequency response are required. Are we going to measure acceleration from DC out to X amount of hertz, or are we going to start at some frequency above DC and need to go out to several thousand hertz or even beyond? Mass loading effects. The accelerometer has mass, and depending on what you're testing, that mass can influence the dynamic characteristics. So we want to make sure that we understand the mass of the accelerometer, how it affects the actual end use and the data. And of course, in some applications, it's a major concern. Other applications, it's not a major concern. Then looking at trying to filter out some of the undesired content. Undesired content includes things like transverse acceleration that influences the measurand, temperature effects, mounting effects. So understand what are those effects and which ones we need to do to minimize it. Then sensor mounting method. Sensors can be mounted, can be either stud mounted, which is generally preferable for high frequency response to get a good energy coupling. Then, of course, adhesive mount, which does a great job as well, which is very common. Magnetic mount also is being used. And there's other mounts involved regarding industrial accelerometers like probe mounting. Then the next selection criterion to look at is cable selection and length. Cables are the weak link in any measurement chain, and there are quite a few cable choices that are available from various manufacturers.
Has joined the meeting.
Guide with that issue. Then lastly, signal conditioning in data acquisition systems. The accelerometer is either going to need to be powered or need associated charge amp, depending on the model. And then that data is going to be typically collected either or viewed on the oscilloscope or recorded via data collector. So it's just kind of a initial starting point from start to finish with regard to selecting a proper accelerometer and things to think about when doing so. So moving forward, let's learn about I apologize for that. It was an amber alert. Excuse me for that. So moving forward again, looking at types of acceleration, and that is going to include constant acceleration, which of course would be something similar to due to Earth's gravity, or centrifugal forces that are associated with a constant rotational speed. For the most part, PCB does offer sensing options for all of these selections, and we can talk about that. We're going to focus on one particular subset of accelerometers, but we can provide product to measure constant acceleration. Next one is transient acceleration, or a singular event like a shock event or a collision event. So transient, just a singular event that has amplitude and duration. And then periodic acceleration, which is more typical, where you have acceleration that occurs at various amplitudes and frequency over a long period of time, such as in rotating machinery. So periodic acceleration, of course, as a result of continuous motion, and that's the more common use of accelerometers are events that are relatively continuous for some defined period of time. So what types of accelerometer technologies are available to you?
Has left the meeting.
Yeah, piezoelectric accelerometers are predominant from a dynamic measurement technology. We have, or they're offered on the market, we refer to as ICP technology, where you have a piezoelectric sensing element with onboard electronics to convert a high impedance output signal to a low impedance voltage. Then piezoelectric sensors that are charge output, typically used for higher temperature applications. Then MEMS-based accelerometers, which are designed predominantly for your constant or low frequency applications. Capacitive accelerometers, and resistive element accelerometers. So those are the type of technologies that are available to you. We're going to focus our presentation this afternoon predominantly on piezoelectric accelerometers, and if you have questions regarding the other technologies, just let us know. We'll be glad to answer those, but we're going to focus on piezoelectric. So let's take a look at transduction.
Has joined the meeting.
So transduction is how do we convert a mechanical energy, in this case motion imparted into the base of the accelerometer, and convert that into a usable electrical signal that has meaningful relationship to the mechanical input to the transducer. So in the case of an accelerometer that's piezoelectric in nature, we have something referred to as the piezoelectric effect. So in this case, the bottom gray bar represents where the sensor is mounted, and then motion's imparted typically through the base of the accelerometer, and that motion results in force being applied to sensing elements and that results in an output referred to as a picocoulomb. And that picocoulomb then is representative in amplitude and frequency to the event that it's trying to be measured. And the mass, of course, on top of that allows us to induce that stress on that associated crystal. And then, of course, F equals MA with regard to the nature of the design of the product as a free body. So let's take a little closer look at sensor element technology and how the sensors are structured from a design perspective, and again, governed by Newton's second law of motion, F equals ma. So taking a closer look here, we have our base of our accelerometer located where this black line is, and then we have a post, and then we have a sensing element shown here in yellow. And that sensing element is, in this case, is an annular shear design. And that sensing element can be naturally occurring piezoelectric material like quartz, or could be using man-made materials like ceramic elements. And then there is a mass that surrounds that piezoelectric element, and then there's a ring that goes around it to compress it and preload, and then, of course, when motion's imparted, that mass places the crystal or sensing element into shear, producing an output. And that output, of course, is directly pursuant to the mechanical stimulus that the sensor is exposed to. So again, that's Newton's second law of motion, F equals ma. So let's take a look at characteristics of accelerometers and how they're derived. And so upper frequency response of an accelerometer is typically a result of the mechanical characteristics of the accelerometer as it relates to its overall mass, stiffness, and then overall its resonant frequency or ringing frequency. The two graphics below, one to your left, is a free body diagram of an accelerometer where we have a seismic mass acting on a sensing element shown here as a resistor. Then next to it is a filter, and that may or may not be applicable depending on the sensor model number. And that will provide filtering of high frequency content that typically is undesired, or depending on the sensor technology, could be allowing to mitigate some of those other undesired characteristics that you may not want to see. So ideally, looking at the plot to the right of that, we have a plot of the natural frequency of an accelerometer relative to amplitude and frequency. And that filter, whether it be low pass, two-pole, single pole, will tend to mitigate that dynamic influence in the measurand by mitigating that high frequency response, providing a better or broader band of measurand with regard to frequency. So let's take a look at what governs the low.
Has joined the meeting.
Take a look at what governs the low frequency response. Low frequency response is governed by the electrical system of the transducer, and that relates typically to what we refer to as discharge time constant. And discharge time constant relates to the rate that the signal discharges back towards zero.
Has left the meeting.
Characteristic of piezoelectric sensors, they're going to respond to mechanical stimulus, and when the constant acceleration is experienced, their output decays back towards zero. Although this presentation does not get into the detail of discharge time constant, but be aware of it and be aware of effects of AC and DC coupling, and those are things we can talk about at another presentation if desired. But essentially, again, as a quick summary of this slide, low frequency response governed by the electrical factors associated with the transducer, and those can be defined by the -5% as 0.5 divided by the DTC, which is a spec on the transducer specification sheet. And then, of course, 3 dB down would be 0.16 divided by DTC. So it gives you a feel for the low frequency response characteristics of an accelerometer. Now let's put it all together and take a look at the entire bandwidth plot of a typical accelerometer. And here we're looking at the low frequency roll-off on the far left, and to the far right, we're looking at high frequency effects on that. And the sweet spot is the linear portion of that plot, which is shown here as ±5% and ±10% range. For your reference, the flat linear response characteristics typically occur at 20% of the sensor's mounted or resonant frequency. So just to give you an idea where the linear characteristics are. When you're acting above that or below that, you can have errors introduced into the sensitivity, producing errors in your measurement chain. Those are typically provided in calibration data reports, so you can understand how frequencies out beyond the linear zone affect that measure and accuracy, and even below as well. So I just want to make sure I tied it all together into one plot to allow you to look at effects of low frequency response and high frequency response of a typical accelerometer. So what are some of the undesired responses that would affect the measurement or the fidelity of that application? Thermal transients, and of course thermal transients would be not a soaked environmental change, but a large change in temperature that occurs over a short period of time, and the sensing element material and the construction of the sensor element controls and dictates how that sensor responds to temperature. Then you have off-axis, whether we're measuring just simply the z-axis or x, y, and z, there is influence, in this case transverse for an example, that may influence that measurement. Base strain is as a result to the mounting of the transducer. When the accelerometer is mounted, particularly when stud mounted, which requires torquing in place, excessive torque can result in base strain that influences that sensor. However, most modern accelerometer designs, which are shear versus the old designs, which were compression nature, are nowhere near sensitive to base strain as they were early on. The other influences could be electromagnetic interference from AC fields. The sensors are relatively insensitive to DC fields, but when the AC fields are present from large electric motors, or as in a maglev or railgun type applications, you'll see that there is influence in those sensors, and special construction techniques have to be applied to mitigate the majority of that. Radio frequency interference, other airborne influences, those generally influence the cable. The cable is an antenna, essentially, that runs between the transducer and its DAC or power supply. So low noise cables combat that, and certainly off-ground mounting the accelerometer combat that as well. Magnetism, such as in a medical instruments, can influence that, so certainly certain materials need to be considered if used in those environments, particularly materials that aren't subjected to or cannot be magnetized, like the Modal family. Sound pressure, depending on the level of sensitivity, if you're looking at seismic level acceleration events that are, sub 1G, certainly sound pressure can influence that as well. So hopefully that's of value. We'll go ahead and move on to the next slide. So let's take an overview of accelerometer construction. Let's expand it to the point where what you actually see, what a full accelerometer looks like, housing, connector, and entire assembly. So in this case, it's a single degree of freedom, or one axis, and we have our base of our accelerometer, which has its post and has its annular shear sensing element with seismic mass, which of course excites that sensing element in shear to produce an output referred to as a picocoulomb, or millivolt per G, or millivolt per meter per second squared. And then on top of that, you may notice an electronic circuit that's referred to ICP microelectronics. ICP is an acronym. ICP is an acronym for Integrated Circuit Piezoelectric. That happens to be a trademark of PCB, but essentially that converts the high impedance picocoulomb output of the sensing element to a low impedance voltage output, such as in millivolts per G. Today, 95% of the accelerometers that are used today are predominantly going to be sensors that are ICP type, that have onboard electronics to give you a low impedance signal. An advantage of that is a high level output, typically 5 volt full scale, and also allows you to use lower cost cabling and give you a cleaner system, not as sensitive to other effects like contamination, dirt, etc. So just give you a quick overview of what an entire accelerometer looks like from a cutaway perspective. So let's take a look at accelerometer mounting methods. So starting in the upper left-hand corner, we have a typical accelerometer. In this case, that is stud mounted. So the accelerometer either has a male or female tap-threaded hole, and then through use of a supplied mounting stud, the sensor is secured via stud, and that allows a very good coupling of energy between the mounted surface and the accelerometer. Hence, it allows you to get out to extended frequencies. And that's represented by the chart to the right. And taking a look at the 352C34 stud mount, we've got frequency response characteristics well beyond the capability of most accelerometers. Then adhesive mount, very conveniently used because you're not required to modify the object you're mounting the sensor on. That way you don't damage it. And those adhesives are typically very commonly used and
has joined the meeting.
Applied by the sensor manufacturer. Easy to apply, and many sensors are adhesive mounted directly, or you can take stud mounted accelerometers and adhesively mount through a mounting pad, which in many cases is a supplied accessory. And looking at adhesive, that will cover frequency responses also well into the capability of the accelerometer. Most accelerometers' typical response characteristics run between 1 and 10 kilohertz. There are exceptions, of course, on the low and the high frequency side, but certainly adhesive mounting will cover the majority of your frequency response requirements. And then looking at the next option for ferrous surfaces, we do offer magnetic mounting options. That's a very quick, simple installation, generally short-term use, and that certainly allows good characteristics. In this case, out to several thousand hertz as well. And the other option is that's not shown here pictorially is mounting sensors on mounting blocks, and that also generally expresses response characteristics out beyond the characteristics of the sensor for the most part. So I wanted to give you an idea of what are the mounting methods and what's the influence of those choices from a frequency perspective and also from a perspective of how it influences your test article. So next slide talks about cable consideration. As I mentioned earlier, cable is a weak link in the measurement chain, predominantly because they can be damaged early easily by being stepped on accidentally or due to fatigue over time if not properly stress relieved. So there are two types of sensor technologies that we've been talking about, being piezoelectric, being charge output sensors. Those have no electronics on board and generally are good for higher temperatures. Generally, a lower noise cable requirement exists where we eliminate what's referred to as the triboelectric noise effects of cable movement in charge mode systems. And, of course, longer cable distances can be problematic, and there are steps to take to account for that. With the ICP systems, being a high voltage, low impedance output, they're well suited for longer cable runs and simply can account for longer cable runs by using higher constant current, which we've not discussed in detail here. To your right is a chart and also formula that you can use to calculate the influence of cable capacitance, and its influence is it can mitigate frequency response when the cable length exceeds, say, 100 feet or so, which it does in specific applications. And in order to understand that it's not a frequency response mitigator, we will look at cable lengths, cable types, capacitors of the cable, and looking at the voltage output of the sensor, which is part of that formula, as well as its capacitance. And then that's really a discussion to itself at times, but something I wanted to at least touch on to give you an overall view of making sure that you take the cable into consideration with regard to its durability, suitability for the application, and the environment that the sensor is going to be used in. Moving on to the next slide, what sensor is best for my application? And I've shown here a wide variety of accelerometers that run from high temperature to room temperature application. So there actually is, 20 to 30,000 different models that PCB offers, for an example, and they come in single axis form, different form factors, some of the geometry, weight constraints. So there's a large selection, and it can be overwhelming at times. So we have developed a methodology to allow you to input various parameters to help narrow down the choice. And our website actually offers a comprehensive online product selector that allows you to narrow down options to key choices and even allows you to compare different models side by side to help you make those choices. So I'm going to take a moment and go to that location. And by the way, it's simply at our core website, but Shop Sensors is where it's specifically located at.
The link. Just go to it. Yeah.
Yep. Okay. Very good. So here is our main website. In fact, let me just go to our main website. This is our main website. So when you go to our main website, just select Shop Sensors is where that link took us. So Shop Sensors. So here is basically an online store that allows you to find, compare, and shop for accelerometers. So in this case, we're going to go ahead and look at accelerometers test as an example. So we've selected accelerometer test, and it brings up options for you to consider when selecting accelerometers. And so there are some key points to take a look at. Type of sensor output, be voltage, meaning ICP, which is piezoelectric, or MEMS-based accelerometers, or charge-based. You can choose either single or three-axis. You can choose even TEDs. TEDs, which we haven't covered, essentially is a transducer electronic data sheet from a specific definition. But essentially what it is, it's a double EEPROM that's on board the transducer that actually stores pertinent data of the accelerometer. That includes model number, serial number, sensitivities, calibration dates, etc. And when you use a TED-enabled signal conditioner or TED-enabled data acquisition system, that will look at that double EEPROM on the sensor and automatically recognize that sensor and scale that measurand based on the sensor sensitivity. So it's highly desirable in high channel counts. That way you don't have to go into each individual channel on a DAC system to enter specific serial number sensitivities. So very convenient for a high channel count. The next thing to look at is temperature. We offer quite a range of temperatures, temperatures even up to 1300 F, and also down to cryogenic as well. So this gives you a selection. Also, the next criteria to take a look at is electrical isolation. If you're mounting the sensor on a surface that has electrical potential, you may want to choose a ground isolated sensor to avoid having 50 or 60 cycle influence that data. Then accelerometer mass, that's available here as well. The next criteria to look at is what is the minimum frequency response you need. 0 hertz would be, of course, a MEMS-based type sensor, but typically piezoelectric sensors certainly can be suitable for lower frequencies too. So that's availability for you. Sensitivity in terms of millivolt per G. That, of course, relates to your application in terms of magnitude of acceleration that's expected. Whether we need something that's simply 10 volts per G, like in a seismic application, or in a shock application where we're looking at, say, 1 volt per G or even less for those higher magnitude events. Incidentally, you can select metric units if you prefer, and that, of course, will give it to you in terms of meters per second. Just make you aware of that as well as temperature. I'm going to go back and switch back to English for this purpose of this presentation. So, pardon me. So looking forward further on selection criteria, min temperature, also electrical connector position. The sensor is going to have an electrical connector. Where's the best exit location for that? We can have units that are, provide a side connect or radial if we prefer, top exit, bottom exit, or even integral cable options that are available to you. And then your maximum frequency you expect to have to measure, your expected max G range in this case, and also your mounting type that's preferred, whether it be cap or stud or adhesive. Or even surface mount type of sensors. The other thing to consider is sealing. You can see most of our accelerometers in this case are hermetically sealed. And hermetically sealed accelerometers are usually verified with regard to its hermeticity. And they're generally by itself impervious to contaminants such as dust, dirt, etc. And with a proper cable connection, they can be used in splash conditions and even used underwater for periods of time. Other types of sealing methods would be epoxy. That's not a large content of it, but either all of our sensors you'll find will be either epoxy sealed or hermetic. Now, after looking at that, let's take a look and populate a couple choices. So let's select voltage. Let's select single. And as you select various ranges, the sensors to your right begin to populate. And there's 111 matches for single axis voltage ICP. And then once you select a sensor that looks right to you, then you can click and get its actual specifications, or even compare multiple accelerometers if desired. So I won't spend much more time on this particular site, but I wanted to make you aware there is a tool that's available to you on the PCB website that helps you narrow down the selection of an accelerometer, or if you need other products, that includes our industrial accelerometers, microphones, force sensors, 420 transmitter, vibration switches, pressure sensors, load cells, torque sensors, signal conditioning, modal hammers. So there's many other products that we can help you with as well, but I wanted to at least focus on accelerometers for this purpose of this presentation. So let me go back to the presentation. All right, so let's move to the next slide. So looking at product testing or research development of piezoelectric accelerometers, why do we test products? What are the goals of product testing? Typically, we want to substantiate design concepts, to test product survivability, ensure that it meets proper performance criterion, ensure consumer acceptance, weed out potential defects. Now, what are some of the methodologies that are employed? Vibration stress screening is often employed in electronic componentry. Accelerated life cycle testing, we've got a component that you can actually accelerate its testing and simulate X number of cycles in order to shorten that testing cycle. Shock and drop testing, we're actually dropping a product or dropping a package. Package testing in itself, that alone is quite an art. And so this gives you an idea of some of the things you may want to look at when looking at using accelerometers in research development. Why would you use them, and what are the kind of methodologies you might want to use to get there? So looking at what are the typical applications that we or you use these products for, and that includes typically structural testing, that includes modal analysis, which we haven't talked about, product testing, research development, vehicle endurance or ride simulation testing, seismic monitoring, that would be looking at structures such as bridges, buildings, or even monitoring earthquake events or monitoring for them, engine vibration, for an example, quality assurance, noise vibration and harshness, and accelerated life cycle. Some of the applications that these products are being used for. So I do have one application that you might be interested in. So here's an application. In this case, customer wanted to measure the vibration event that occurs in the rearview mirror of an automobile as a result of car being driven, of course. And the customer provided some parameters, and those parameters were vibration less than 50 Gs, frequency range between 1 and 300 hertz. You wanted to do an adhesive mount, can't really stud mount on mirror or glass, and you needed a very low mass accelerometer because a large mass, of course, would change its characteristics and it would dampen those characteristics. And testing needed to be conducted in a vehicle over a wide range of temperature. So the sensor we ended up recommending was an adhesive mount accelerometer that we refer to as a teardrop. In this case, it was our model 352-824, and that provides 100 millivolt per G. It's an epoxy sealed sensor. So in this application, the environment's rather benign, so we don't need a hermetically sealed sensor, and its mass is quite light at 0.8 grams. So this sensor, adhesive mount again, it is a very small electrical connector, 356, again to minimize that mass. In this sensor, it was an ICP sensor, So meaning it had onboard electronics that convert that high impedance output of the sensing element to a low impedance voltage, which is typically normalized at 5,000 millivolts full scale, or 5 volts if you prefer. In this case, that sensor is good for minus 65 to 250 F. So just a quick overview on a application and selection of a product as an example. So with that, that kind of includes the overall presentation, and I'd be happy to entertain any questions that you may have at this time, or if you prefer, you can contact me at my email address, kwatkins@pcb.com, and I'd be glad
Has left the meeting.
Be glad to answer those individually.
We do have one.
Go ahead, please.
What are the extreme
Has
temperatures
left the meeting.
of piezoelectronic accelerometers? Extreme.
The question that got submitted was, what are the extreme temperature limits of piezoelectric accelerometers? Piezoelectric accelerometers have been used for temperatures down to cryogenic, which is typically minus 320 degrees Fahrenheit, and which is commonly used for certain applications specifically involved in rocket motor fuel pumps, fuel chambers, etc. Higher temperatures, we have accelerometers in our catalog on our website that are good to 1,200 degrees Fahrenheit. In actuality, their product could even exceed that. So to answer the question, the extreme parameters from a catalog perspective are minus 320 degrees Fahrenheit to 1,200 F. However, there are products used beyond those temperatures on a more specialty application. So I hope that answered your question.
And just one more. Respective of adhesive-mounted accelerometers, what adhesive is typically recommended?
So looking at adhesive-mounted accelerometers, which was the question, is which are very popular choices and which do not permanently mar the surface which the sensor is mounted to. We generally recommend a product offered by Loctite. It's model number 454, and that essentially is a gel-based super glue that's used to bond the transducer to the test surface on a temporary basis or even some longer-term test. And that adhesive is used to allow you to quickly install the sensor, and it can be easily removed using a removing agent like acetone, which will soften that material, and you can twist the sensor, and we do provide tools that allow you to do that quickly. So adhesive mounting using Loctite 454 is what I would generally recommend for adhesive mounted accelerometers. In many cases, many accelerometers that are supplied that are intended to be used as adhesive mount only do include the adhesive as a supplied accessory. So hopefully that answered that question as well.
Excellent. Let's go to the last slide. Thank you, everybody, for attending the webinar today. You can always go to pcb.com/training for our upcoming webinar series, and also stay tuned for upcoming acoustic and modal seminars that we're busy scheduling right now for 2019. So thanks, everybody, and have a great afternoon.
Appreciate it. Thank you.
Has left the meeting.
Kevin.
Has left the meeting.
PCB.
Has left the meeting. Has left the meeting. Has left the meeting.